Hi, so this is my video on parametric curves, right? So let's try to understand what a parametric curve is. So first of all, we'll start in college algebra. We'll start where we define functions and take the simplest of functions here. So, well, this is a function, right? Okay, which is actually the part of a parabola, a sideways parabola. But if you take the whole thing, right, then this is not a function. Why? Because it violates the vertical line test. It's not a function. So what happens is we still want to do calculus with it. We want to do arc, we want to find arc lengths, we want to find centroids of laminas which has a parabolic surface. We want to do all kinds of things with it, right? But almost all of the formulas that we have for arc length and centroids and all those and basically calculus, deal with the fact that we need actually a function, right? We need y as an honest function of f of x, but we don't have it here, right? Okay, in this case. So we use, but we do, so that's one reason that for one logic for the parametric curves, right? Also, like if you take a parametric curve like, like a curve like that, right? Let's take another example, okay? Second example, let's take a circle. Once again, this is not a function, right? This is not a function. Why? Because it violates the vertical line test. So, and then if you just, even if you write it as a function, say, x squared plus, so say, x squared plus y squared equals, say, 1, and then you write it as y equals 1 minus x squared, you don't get the whole function, you only get half of it then, right? Okay, so you don't get the full circle. But and then somebody might say, let's do implicit differentiation, right? And we can do calculus on this still, right? Okay, but there's another problem. Suppose this is a cycle race. Suppose there's a bunch of cyclists going around this circle, round and round and round. Now, so you cannot, for all the cyclists in the race, you will still have only this one function, which is not fair. Because somebody, there could be the leader of the pack, right, who will be geometrically very close to the last of the pack. But in the geometrical figure, they might look as if they are really close, but there are several laps apart. The leader is leading the second one by several laps. So how do you represent the motion? That there could be several laps. Okay, so that's another right motivation for parametric curves. So so let's go back to the parabola. Okay, so let's go back to the parabola where we have this. Okay. Now, I'm going to ask you to keep that in mind, and I'm going to actually to do something like that, right? Instead of writing y equals f of x, which we cannot do, what we are going to do is we are going to write x and y both using a third variable, a third party variable. So let's take the variable. So let's consider a third party variable t, right? We call it the parameter, right? Meter, right? And let's define y is simply t. Okay, all right. But now we need to define x. We know that this is actually the equation of this curve is not really y equals square root x, because they only get the first part. But if you square both sides, you get y squared equals, and then that is the equation of this curve, which covers both parts. So we do have an equation in rectangular coordinates, which is y squared equals x, the familiar curve. Now, suppose you put y equals t, where t is a parameter. Then this y becomes t squared, and x is automatically set. So x will be t squared. So what we do is x equals t squared. So I want you to look at this. So really what we have done is we have written x and y separately using a third variable called t, which is called a parameter. So this is a parametric representation of the curve. And actually, if you don't have this, right, if you just have this, you can still get the curve. How? Well, you can eliminate t and get this, or you can also plot points. So let's put t and x and y and see what you mean, right? So when t is equal to say 0, x is equal to 0 and y is equal to t, which is what? X is equal to t, so this is t squared. So y is equal to 0. So t is equal to 0, y is equal to t, that's also equal to 0. So you get 0, 0, the point, which is what? This, because this is the point. Now let's put t equals 1. If t equals 1, x equals t squared. So x equals 1 squared, which is 1. And y equals t, which is also 1. So you get another point, 1, 1, which is also here. Okay. And let's put t equals 2. You get what? X is equal to t squared, which is 4. And y is equal to 2, t, which is x is equal to t squared, which is 2 squared, which is 4. And y is equal to t, which is 2. So we got another point, 4 and 2. That is 4 and 2. Here, but so 1 and 1. But let's try to put a negative value for t. So let's put negative value for t. So if t is equal to negative 1, you know that x is equal to t squared, right? X is equal to t squared. So you put negative 1 here, you get negative 1 squared, you get positive 1 again. And y is equal to t, so y is negative 1. You get another point, 1 is negative 1. So you can see that you actually get the point here. So not only you get the point up, but you also get the point down, which is nice because this is not a function, but it still gives you all the points. And now if you put t equals negative 2, you get x is equal to t squared, which is 4, and y is equal to t, which is negative 2, and you get 4 negative 2, and which is nice too because you get this point below, which is 4 negative 2. So as you change t to positive and negative values, you can see that you can actually get the entire parabola. So this is a pretty cool representation, right? Okay. And then that's a parametric representation of a parabola. Okay, a full parabola. Okay, now let's do an example. Explain or describe the curve given by the parametric representation. X equals cosine theta and y equals sine theta, and t, now you are giving t a range. So let us method 1, right? Let's just plot points, right? Just for illustration, this is good, right? Plot points. Okay, so we have let's say we want to put some values for t, and then we get x, and then we get y. Okay, so we start the value for x0. So if you get t equals 0, you know that cosine 0, so this will be cosine 0, right, which will be known as 1. And what is y? Y will be sine 0, which is equal to 0. So the point will be 1, 0. Okay, so let's go to a corner and we try to sketch those points. So that's 1, 0. So if we call this 1, right? So this is actually called the initial point, right? There's a name for that. We call the initial point, right? That's where it starts, right? You need to keep track of how it goes, right? Okay, that's the initial point, and then we go to the next point, which will be, so what shall we select? So we need to go from 0 to 2 pi, the unit circle, right? So maybe the next point might be a good idea to take 30 degrees, so unit circle angle, so pi over 6. Then we have cosine pi over 6, right, which is what, square root 3 over 2, and sine pi over 6, which is 1 half. So yeah, square root 3 over 2, which and 1 half, right? So square root 3 is say 1.73, I think, I don't know, and you divide by 2, you get 0.86 something, right? And so it's something like 0.86 and 1/2, right? So this is your, so if it's t equals pi over t, so we get, something like this, or square root 3 over 2, right? And then let's try pi over 3 then, right? Okay, the next one, you can try pi over 4 also. So cosine pi over 3 will be 1/2, and sine pi over 3 is square root 3 over 2. Once again, that will be that 0.86 thingy, right? Okay, so now you have the point 1/2 uh, and then 0.86 something, right? So now that will be, so if this is like 1, this will be like 1/2. So we are talking something like this. You can, you can see that it is taking the shape of a circle, but we can kind of clarify that. If you take pi over 2, then we have cosine pi over 2, which is 0, and sine pi over 2, which is 1. Okay, so so this goes up to here, right? Okay, so we have then 0 and 1, and that confirms our suspicion. So as t goes from 0 to pi over 2, this curve goes from 0 to 3, and then you will know what's going to happen, right? Okay, you can put some other points and see for yourself, right? Okay, so if you put pi here, then you get cosine pi is equal to -1, and the sine pi is equal to 0. Okay, so then you get to here. Okay, and then if you put 2 pi over 3, we know that cosine 2 pi over 3 is 0, and sine 2 pi over 3 is -1. So you get, so this is -1, 0. So this is 0, -1. So you get this point. And finally, if you put 2 pi, cosine 2 pi is 1 and sine 2 pi is 0. So you once again you go back to this. So as t goes from 0 to pi, this curve actually traces a circle. Well, kind of weird, but you can think of this as a circle, right? Okay, not very good at drawing circles. So you actually go through a circle. So that is method 1. So method 2, you try to eliminate, what you do is you try to eliminate net t. So we have x equals cosine t and y equals sine t. So you try to get a connection between the cosine and the sine from which you can eliminate the t. So we can do that, and because we know that cosine squared t plus sine squared t is equal to 1, so which will actually tells you that x squared plus y squared is equal to 1. So we eliminated, but we know that this is an equation of a circle, or center 0, 0 and radius 1, and which is the same answer. So you, from both methods, you can actually get the same answer. So you need to be careful, right, when you are doing this, right? Okay, because see, now just take an example. So let's take my example 2 as this. So let's take x to be equal to cosine 2t and y to be equal to sine 2t. So if you just, so once again, if you want to get a connection between these two, you get cosine 2t plus sine squared 2t equals 1, which is what? X squared is plus y squared is equal to 1. And you say it's a circle. Yeah, it is a circle, but let's see really what happens, right? Right? You might be able to put some points and see. So let's take t and x and y, and so and see what happens. So if you put t equals 0, cosine 2t is equal to 1, cosine 0 is equal to 1, sine 0 is equal to 0, you get 0. Let's just go to pi over 2 right away. Cosine 2 pi 2t would be equal to cosine 2t is cosine 2 pi over 2, okay, which is cosine pi, which is -1. So cosine pi over 2 is, so when when t is equal to pi over 2, you get x is equal to -1. Sine sine, if you put sine 2t and put sine 2 times pi over 2, again you get sine pi, which is 0. All right, so you get -1 and 0. Okay, where is that? And that is here. So guys, when t goes from 0 to pi over 2, it's not here, but it has actually crossed half the circle. And then you can see that when it goes to pi, see what happens. X is equal to cosine 2 theta, so cosine 2 times pi, which is 1, and y is equal to sine 2 t, so which is equal to sine 2 times pi, which is 0. So you're already at 1 and 0. You're already here. So when, what I'm trying to say is when theta, so let me write that down. When t goes from 0 to pi, we have already done one circle. So if you go from 0 to 2 pi, I'm sorry, I should have written that before, right? Okay, if you go from 0 to 2 pi, what do you think will happen? 0 to pi, one circle means between t, the curve goes around the circle twice. So that actually tells you one of the reasons for parametric representation, right? Okay. So once again, if you go from t from 0 to pi, we go around one circle, right? But if you take from 0 to 2 pi, right, the curve goes around the circle twice. So this is actually another justification why we use parametric circles, because if we just use the rectangular equation, you just get a static circle. You don't see the motion. But now when t goes from 0 to 2 pi, you know that this is really a myth, because there's no one circle. You go around the circle twice, like a cyclist going around the track twice. So you need to be a little careful when we do that, right? Okay. All right. And so that's it for this video. I'm going to see you in another video. Thanks for watching. Okay.